Well, in the last video we looked at the oscillator that we're going to use to derive Leeson's equation briefly, but before we go on and derive the equation in this video, I think we just need to look in a bit more detail at the vectors around the loop and some of the precise ways in which the oscillator works. So this is the same block diagram that we're always talking about. So the noise vectors very simplistically look like this. We have a feedback vector, to that is added the noise at the input of the amplifier, and this resultant is the input to an idealized amplifier that has no noise in it. But actually the noise is very much smaller than the other two vectors, so we've changed the proportions here so we can see it. So if we look at this in a bit more detail, so the extra information we've got on this more detailed diagram is we can see that the feedback vector and the resultant vector here are very much longer than these other two vectors. These look parallel, but what I'm trying to represent is these do go down to a point that is way off the bottom of the page. They do meet. So what we're looking at here is a very expanded view of just this bit of the top of the vector diagram. So yeah, these two vectors are really virtually parallel. Now also we've split the noise up into two components, the in-band noise and the out-of-band noise. Actually there's not a completely clear distinction, but noise that's well inside the oscillator bandwidth is processed differently to noise at a higher frequency offset. So first of all, let's consider what happens to noise well inside the oscillator bandwidth, and by the oscillator bandwidth we're talking about the bandwidth of the resonator, which has been vastly reduced by the effect of positive feedback. So nothing to do with this vector diagram, but because of the way the feedback system works, it's working as a very narrow band high gain amplifier. This in-band noise will be simply amplified by the system and will appear at the output as an amplified version of itself. This vector here, the resultant, is the input to the amplifier, and remember it's an ideal amplifier, so the output of the oscillator is just this multiplied by whatever the gain of the amplifier is. So if this noise changes in amplitude or in phase, this whole vector diagram will follow it. This moves 1 degree clockwise and the whole vector diagram will move 1 degree clockwise. And this increases in amplitude by 1 dB and this increases in amplitude by 1 dB. Of course, if we've got a practical oscillator with limiting in it, then of course that won't happen. Now at the other extreme, let's consider what happens to noise at very high offset frequencies. Noise at the noise floor of the oscillator. Now here we're so far away from the bandwidth of the feedback system that the feedback system doesn't follow at all the noise. So if this out-of-band noise was to move, say, over so it pointed out like this, then of course this resultant would move over here because it would follow the laws of the vector diagram, but the feedback vector here wouldn't change at all as a result of the out-of-band noise. So you can see a complete difference there. Now the region we're interested in, the Leeson, the region governed by the Leeson equation, the minus 20 dB slope against offset with offset from carrier frequency. This is the region where the effect that the out-of-band noise has on the feedback vector varies throughout that region. If we're only just outside the oscillator bandwidth, then the feedback vector will follow to some extent the movement of this out-of-band noise. If we go out close to the noise floor, then the feedback vector will have virtually no dependence on the outer band noise. And bear in mind, this is normally represented on a logarithmic scale, and there's a vast difference in influence that this outer band noise has on the feedback vector across that range. So it is this in-band noise that is amplified up to limit level in a normal practical oscillator, and the bandwidth of this noise is actually important to the derivation of the Leeson equation. That derivation, in fact the whole Leeson equation, relies on this being a specific bandwidth related to other things in the system. Now I ought to say a bit about flicker noise. The Leeson equation we're deriving is not connected with the flicker noise region, but I need to justify why we haven't considered it in what we've just been talking about. I'll explain why, just in case there's anyone who's not absolutely furious with me for not mentioning it. So this is the minus 20 dB per decade slope, the Leeson slope, and in our simplistic model this will go up, and at the oscillator bandwidth, say that's here, the plot will then go horizontally at a constant power spectral density to zero frequency. But what happens in a practical oscillator is at some frequency, the flicker corner frequency, there are other more complicated effects that cause the noise to go up. Say that's about here, so actually the plot will go up like this, and then closer in it will get even worse. So the point is, we're basing our whole analysis of the oscillator on something that is actually apparently being disrupted by the flicker noise. So I'll just explain what happens, because it seems that this doesn't actually cause a problem with the way the derivation works. First of all, it's important to understand that a resonator can be modulated at a much higher frequency than its bandwidth. The bandwidth associated with the Q of a resonator, or even if we have a positive feedback system increasing the Q, that bandwidth doesn't limit the rate at which we can modulate it. To give a practical example of this, supposing we consider something like a pendulum, a mechanical oscillator, and if this pendulum has got a very high Q, let's say it operates in a vacuum and it has magnetic bearings, so there's virtually no loss. So if it ticks once a second and it can run for a year, say, and only be 3 dBs down, it's got a very high Q and a very narrow bandwidth. The bandwidth is associated with that period of time it can run for. But we know that while it's running, if we were to instantaneously increase the mass of the pendulum while it was swinging, then in the next cycle the frequency would have changed. So you can see, if we modulate the resonant system, we can we're not limited by its bandwidth. Well, this is what flicker noise is doing with the resonant system in the oscillator. Flicker noise is a noise modulation of the phase shift in the amplifying device, and this is something that's closely linked with the whole resonant system, because the positive feedback is connected with the resonant system and can pull the frequency. So we can consider superposition here. What's happening is the oscillator is running, and a very narrow bandwidth, as we've described, is being amplified up to limit level, but actually the frequency that bandwidth is centered on is being modulated by flicker noise, but it doesn't actually upset the fact that there is this narrow bandwidth. Now, another thing I just wanted to clarify before we go to the derivation is the way AM and PM can be represented by sidebands. So here we have a simple clock face, a clock with two hands on it. One hand goes round anti-clockwise and one hand goes round clockwise, both at exactly the same speed. So it's in exactly the same way that the two vectors of the upper and lower sideband move in relation to the carrier. The carrier is stationary on the vector diagram, but the upper and lower sideband are identical frequencies above and below it, and so they move at exactly the same speeds in opposite directions. So you can see with this arrangement, these two hands cross at 12 o'clock and they cross at 6 o'clock. And at this position, the two vectors add and point upwards, and at this position, the two vectors add and point downwards. When the two vectors are pointing out here horizontally, they cancel out, but at all positions, no matter where they are, the horizontal components always cancel out. So we have these two vectors which are producing amplitude modulation. They move the resultant of the carrier up and down, but they don't produce any phase modulation. Now, if we change the phase relationship of these two sidebands like this, one still going round clockwise and one the anti-clockwise at exactly the same speed, but now they cross at 9 o'clock and at 3 o'clock, and here the resultant of the two vectors points to the right, and here the resultant of the two vectors points to the left, but at all positions the vertical components always cancel out. So we can see that depending on the phase relationship of the sidebands, we can produce either AM or PM. So it's like this on the vector diagram. Of course, if you have just one sideband, then it will produce both AM and PM. Now, a useful thing this takes us on to is the way that phase modulation by noise of the carrier can be represented in terms of sidebands. In the derivation of the Leeson equation we're going to do, we're considering the noise in the active device just as a noise figure. The noise in the device is characterized purely by its noise figure. Now, it is okay to do this, but it's more complex than just the published noise figure of the device, the noise figure that would be the parameter to use in the case of a low-level amplifier, because there's another completely different noise mechanism where the phase of a high-level carrier can be modulated by noise. Now, in the flicker region it's more complicated, but when we're just talking about broadband white noise, then really this phase modulation of the carrier can be seen as additional noise sidebands that add to the noise figure of the device. The measurement of the noise performance of a device with a high-level carrier going through it is known as an added noise measurement. It involves putting a carrier into the amplifier, the level that it's going to be operated at, and then measuring the noise in the difference of the phase between the input and the output. So this takes into account all noise sources, both the small noise that would be present in the absence of a carrier and also any noise modulation of the carrier itself. So the noise performance of a device is going to be worse with a high-level carrier in it. How much worse it is will depend on the device. If it's a device that is good in this respect, such as a bipolar transistor or a JFET, then the degradation may not be too serious. With other devices it can be more serious. As an example, the oscillator that we will test out to verify Leeson's equation at the end used a JFET, and the difference in the phase noise that was predicted and measured was 1.5 dBs. That's the height of the minus 20 dB per decade slope. The equipment that was used to measure it, the E5052 correlation analyzer, that's got an accuracy of plus or minus 2 dBs. So you can see it's not too serious with such a device.